and engaging in any potential use of spatial resources. Okay, so just a few comments on the spatial embedding of agents is key for certain types of questions. For example, capturing locality of influence or transmission, insights into certain types of phenomena, concentration of certain things in space, percolation effects, in some cases, spatial reference modes. So when we see certain behavior over space, for example. And spatial embedding is very useful in as much as it GIS. So 2D spatial embedding within Anylogic is provided in two sorts of ways. One way is through the use of continuous spatial embedding, and the other is discrete spatial embedding. I'd like to talk about each of these and distinguish them. Continuous spatial embedding, which is illustrated by a variety of models, including ones we've built up, has no physical exclusion. The idea is that agents are assumed to be quite small compared to the overall landscape scale, and they can exhibit arbitrary spatial density without interfering. That is, they can be located in essentially the same spot, and there's no problem. There's no interference at all. And we've seen this with distributing agents around the space. We didn't really care much if the agents were overlapped in their representation because, as Robin inquired, the agents conceptually are at a point in space. By contrast, there's another form of spatial embedding also supported by Anylogic and illustrated in his, for example, Schelling segregation model, which he showed during his talk, where the space is divided into a set of discrete cells. They're divided into columns and rows, and there's physical exclusion. Only one or zero agents can be in a given cell at a given time. Okay, so there's kind of a physical exclusion. You can either you're here or someone else is here or nobody's here. Now, the Anylogic environment, which was responsible for setting characteristics of the network, also sets parameters for the nature of the 2D landscape: width, breadth, continuous versus discrete, and the character of the neighborhoods that are included. So, if we're gonna take a look at continuous space now. So, if we went to an environment, we'll find that space can be set to be continuous, and in our version of Anylogic, it's a little bit more advanced than the one where I took the screenshot. We have continuous 2D, continuous 3D, discrete, etc. Thick, discrete 2D. In any case, you have a width of that space and a height of that space for this case. You don't have to worry about columns and rows. Those will come in for discrete space. We have a width and we have a height. And that width are measured relative to the origin for the environment, or associated with the population, the embedded population. So if we were to go look at one of these models that we were looking at, let's say by this minimalist network SIR model, you'll find that when we look at the main here, there's a representation shown here in the upper left. Does anyone recognize where this comes from? This representation here? I'm looking at main here. Where does that come from? What? Sorry? Yeah, it's from actually the representation of a person. It looks very similar to what we have for person. But as a kind of heuristic to clue you in to where the origin of the space is, okay? So essentially the space associated with that population is spread out from this point going down and to the right. So if we wanted the population to appear, like right now I have this chart here, right? You see that chart? Chart is appearing in a way that'll overlap with the population. Let me eliminate this my dynamic event. We don't need that sitting around. So I'm going to get rid of it, and then we'll run this model. Fundamentally, though, what we're going to have is a situation where the two are overlapped. That is, the space shown for display people overlap with the space used for this chart. Okay, so if I were to run this, I would potentially uncomfortably see the two of them exhibiting some sort of overlapping, and as a result, get confused as to sort of visually as to what. So sometimes what we do is we move the origin associated with the population. Or alternatively, of course, we could move the chart. So I'm going to run this thing, and we'll see here. Pardon me, saving away the last lecture. It's acting slow here. But what we'll see is a situation where we have the spatial areas overlapped with the. So here are the charts again. And that's because the origin is up here for the location of the population. If we wanted that population to appear in a different area, we could drag down this this visual representation to start, say, below it. And in that case, we would have a displacement which allows the population displayed below the chart rather than atop it. So I'm just going to run that. Wow, it's really slow. And we should see it appearing in a separate space. Okay, so now it's appearing below it. We've changed the origin with respect. Everything, their locations are measured relative to that point, as denoted by that little presentation. Okay, so here we have these sort of continuous. Here we go. So continuous environment, we've seen that. A discrete environment, by contrast, has a specified number of columns and rows. So this space, there's still this space, but it's divided up, it's partitioned up, tessellated into a set of squares, 100 grids horizontally, 100 vertically. Sorry, here's my last lecture. I'd like to suggest we load in the game of life. So there's a model called the game of life, which you can find in the Anylogic sample models. In retrospect, I'm sorry. I think in the interest of time, so we can get to mobility, I think I'll go lighter on this. This is what's called a cellular automaton, so it's divided into spaces, and it uses discrete time and discrete space. So here the space is divided up into cells, and there's 100 rows, 100 columns, and you'll notice the layout type is arranged. Okay, it's arranged. And what that means is it's located in a grid pattern. Furthermore, we have a neighborhood type, which specifies for each cell to whom is it connected. North, south, east, west, northeast, southwest, southeast, and northwest, in addition to those 4 cardinal directions. We have a choice between those two, a Moore or Euclidean. Moore has 4 neighbors. Euclidean has 8 neighbors. Now, in this case, we have 1 cell per grid point. Where else have we seen a discrete representation? Can anyone remember where we saw communication with north, south, east, west? Where else did we see that? Yeah, the grid infection spread that we did up front, right? I'm not going to go into this in great detail, but suffice it to say that when we arrange things at that level of an arranged space, we can line things up in this kind of matrix style, this grid style, and then we have these neighbors within the space, okay? I want to talk, however, a little bit about, well, I talked about time and its model, continuous versus asynchronous before. For the most part, we use asynchronous time. We don't have to worry about a lot of things happening at the same time, because 2 events are rather unlikely to occur at exactly the same time. One occurs before the other. Either you get end-stage renal disease before your death, or you die before end-stage renal disease. Generally, don't have to worry about them in the real world of getting them together, and so it is with asynchronous time. However, there is a notion of synchronous time in Anylogic that supports, and this reflects tradition in agent-based modeling and other packages that things get updated at a discrete level, so in lockstep with each other. And what happens here is, we'll have a distinction between what's called on before step and on step. And fundamentally, the issue here is that we don't want the ordering of with which we update cells to affect the behavior of the model. Suppose we update cell 1 before cell 2 is updated. If they're updated exactly the same time point, same time in lockstep, this is the case for discrete modeling. Suppose we update cell 1 before cell 2. There's the risk that cell 2 will now see the updates of cell 1 and change its behavior as a result. And so it may matter whether we update 2 before 1 or 1 before 2. So the way in which Anylogic avoids that is it provides you a way of collecting information, all the information you'll need to figure out what you want to do before seeing any changes. Step, this thing called on before step, is a time where you can write an action that will collect all the information you need for every cell to figure out what it's going to do before anyone makes any changes. And then, in on step, they actually make all the changes. But it doesn't matter in what order they go then, because the others already have all the information they needed collected before any changes. So there's this kind of separation. I do not recommend this unless you absolutely have to do it, but you will find it for certain models. The truth is that almost all agent-based frameworks that you'll find commercially or you'll find externally, except for Anylogic, it uses this sort of mode where you have lockstep updates, okay? And as a result, you often do have to sweat this issue of what order do you do things in and randomize the order or what have you. Anylogic does provide this on-before step, on-step separation to make it cleaner, but it's still less desirable. I should note in system dynamics, this is kind of what happens. So you read the values of all the cells of all the stocks before any are updated, and those are used to determine the value of the flows. And then all those flows determine the updates to the stocks all at once. You don't have to worry about what order they're updated in. So it turns out that you can enable synchronous time through the environmental page. There's a thing that says enable steps. So if we go to the environment, we could check in the environment. There's something that says enable steps. Okay, here's the environment, and there's a thing that calls enable steps. I'd suggest you not do that, but you'll notice if I do that, it lets me choose how long between steps, and lets me divide the on before step and the on after step. Okay. So this is an example. If you look at the game of life, on before step, it collects information. They called it on step there. I guess maybe now it's called on after step. I'm not quite certain about that. But so here they collect the information, and here they just use the information and update all the cells. It doesn't matter what order they occur in because all the information was collected before. So there's no dependencies in place. So here's on before step. It records the number of ones around and then goes through and actually counts up the number around for a given neighbor, and then it updates it in on step. In the on step, it actually does the update. I don't want to go into this much, but just be aware there are models like that. You use discrete time. They're uncommon. I would recommend you not do it unless you have to. Okay. It's just conceptually, it's much more complex, and Andre referred to this. It's more complex because you have to deal with these so-called race conditions. You have to deal with these competing risks that somehow have to be resolved because they're all playing out in a single sort of unit of time, and you don't know which went before which. It's a pain to have to worry about. Okay, so that was discrete space, discrete time, spatial embedding. I'm now going to talk about mobility. Any questions about this? Okay. So to save that away.